Alright guys, this is section 2-1. Our goal here is to be able to represent relations and graph linear functions. A little bit of vocab. A relation is a mapping or pairing of input values with output values. The domain of a relation is the set of input values. We also call these our x values. So these are our x's. The range of a relation is a set of output values. So these are all of our y values. And a function is a relation for which each input has exactly one output. So the major key thing here, a function, its inputs have exactly one output. So there are 4 different ways we could represent a relation. The first one is through ordered pairs. So these are just normal points that are in ordered pair format, or x value and then y value. The table is just a table of values with x having a column and y having a column. The graph is just a normal old coordinate grid graph with the points or ordered pairs graphed on them. And the mapping diagram is just a diagram where we have input values and output values, and we draw a map or arrows from each input value to each output value. So in example 1, we have to consider this relation given by the ordered pairs. Part A says, okay, identify the domain and the range. So first I want to find the domain. The domain, we said, was all of our x values. And what I'm going to do is put them in these fancy curly brackets, and I want to order them from least to greatest every single time. So the least x value I see is -2, and then -1, and then 1, 2, and then 3. Okay? So here's our domain, all the x values. Now if we want the range, we said, well, that was out of our y values. So the y value is still going from least to greatest in our curly brackets. The least y value I see is -3, and then -2. But then I get to the point where I see 2 1s. Well, I'm just going to write the 1 one time. So if you see any repeated domain or range values, x's or y values, just write them once. And then the last range value I see is 3. That's our greatest y value. So here's our range. So part A is taken care of. Part B says, okay, represent the relation using a graph and a mapping diagram. So what I'm going to do is just graph all of these points on the coordinate grid. So that first one was -2, -3, and then -1, 1, 1, 3, 2, -2, and then 3, 1. So here's all of our ordered pairs on the graph. But then I need a mapping diagram. So we said a mapping diagram needs input values, so I'm going to need input. And I'm going to need output. So the input, I'm just going to put my whole domain, those values from least to greatest, every single time. And I'm going to box those up. And then my output is just my range, or all my y values, from least to greatest. From there, all we have left to do is draw our arrows, or a map. So how I do this is reference back to my ordered pairs and draw my arrows corresponding from each x value to each y value. So -2 went to -3, -1 went to 1, 1 went to 3, 2 went to -2, and 3 went to 1. So there's our map. In example 2, it says, tell whether the relation is a function, and then explain if it is or isn't. So we said back in our vocab that a function is only a relation for which each input has exactly one output. So using our map, we're going to go through our inputs and see if there's exactly one output for each input. So looking at -3, our first input, it has exactly one output, that is 2. At -1, it has exactly one output, that's 3. At 2, it has exactly one output, that's 3. And then at 4, it has exactly one output, that's -4. So, since each input has exactly one output, this is a yes. It is a function because each input has exactly one output. That makes it a function. So, next we have up is the vertical line test. So a relation is a function, so we're testing to see if it's a function or not. It's going to be a function if and only if no vertical line intersects the graph of the relation at more than one point. So, with these two graphs, what I'm going to do is use a vertical line, and I can use as many as I want. These represent our inputs. Okay, so if they cross the graph at one time, like in this first one, that means each input has exactly one output. So that means it is a function. Over here, this one, if I draw any vertical line, it's crossing the graph at 2 points. So this says an input has 2 outputs. Well, that can't happen with functions. This is not a function. So this is how we use the vertical line test to see whether or not a graph is a function or not. Next up, what we're going to do is graph equations in 2 variables. So in order to do this, first thing we got to do is construct a table of values. So our x values and y values. Then we're going to plot those points from the table onto the graph to see a pattern. And then the last step we're going to do is just connect those points with a line or a curve. So in this first example, we're still going to graph. So I need a table. I need an x and I need a y. And what I'm going to do is just plug in the same generic x values. So it's -2 all the way to 2. I'm going to plug those x values everywhere I see an x in my original equation. Okay, so if I plug -2 back into that original equation, I'm going to get back out 3. And then if I plug -1 in there, I'm going to get back 1. If I plug 0 in, I get back -1. If I plug regular 1 in there, I'm going to get -3. Then if I plug 2 in there, that'll give me -5. So these are all coordinate pairs that I can graph on my graph. So -2, 3, I can graph. -1, 1, 0, -1, 1, -3, and 2, -5. So the last step, connect them all for your line, and here we have it graphed. This next one, we're going to do the same thing. So create your table of x and y. We're going to use the same generic x values, -2 through 2, and I'm going to throw 3 in there. So if I plug all my x values everywhere I see x, if I plug -2 in there, I get back 12. -1, I get back 6. 0, I get back 2. If I plug 1 in there, I get 0. 2 in there, I get 0. And if I plug 3 in there, I get 2. So again, these are points. I can graph them. So -2, 12 is going to be clear off of my graph. -1, 6 is on the graph. 0, 2 is on there. 1, 0, 2, 0, and 3, 2. So here we're having a pattern start to come on. So this is look like it's decreasing, and then I'm going to go up and increase. It's kind of like it's reflecting. Okay, so here's my pattern. So this is kind of our U-shaped kind of graph or parabola graph that we'll get to here in a couple chapters. Okay, so here is our graph of this equation. A linear function is a function that forms a straight line. So these only have one x, and they're to the power of 1. So the generic formula for a graph of a line is y equals mx plus b, where m is the slope and b is y-intercept. Okay, so the x has a power of 1. Function notation, a linear function, we're just renaming y as f of x. So this just means we read this as f of x, or f of that value of x. So all we did was replace f of x, the function notation, with y. So for example, tell whether the function is linear. Then evaluate the functions when x is negative 4. So in part A, looking through this function, I see that I have a power of 2. So that is a good hint that this is nonlinear or not linear, because we can only have powers of 1 to make it linear, a linear function. But if I want to plug negative 4 in to x everywhere I see it, I'm going to have f of negative 4, because that's what I'm plugging in for x. And then I'm just going to plug it in everywhere I see that x, or replace it. So if I'm evaluating here, negative 4 squared is 16. Negative 2 times negative 4 is positive 8. And I'm still adding 7. Well, negative 16 plus 8, that's negative 8. Then I'm adding 7 more to it, which is negative 1. So that's what we get after evaluating. In part B, seeing if it's linear or nonlinear, well, I'm looking through here. I only see an 1x, and it's got a power of 1. So this one is linear. Okay, so this one's good. Plug in negative 4 in here. I have g of negative 4, and I'm plugging that in for x. Oops, not 2. So negative 4 plus 8. Well, 5 times negative 4, that's negative 20, and I'm adding 8 to it. So that gives us negative 12 after we evaluate. We're also going to look at section 2-1, the extension. Our goal here is to be able to graph and classify discrete and continuous functions. So different kinds of functions. A discrete function is a function whose graph consists of separate points. Okay, so if I were to kind of sketch one of these out, what it would look like, it's just a graph of some points that aren't connected. Okay, they're broken up. And a continuous function is a function whose graph is unbroken. Okay, so this graph might look like this. Okay, I didn't have to pick up my pencil at all. It was a continuous line that was unbroken. So in this first example, we're going to graph this function f of x equals 1/2 x plus 1 for the given domain. Classify the function as discrete or continuous for the domain, then identify the range. Okay, well, our given domain here is a list of just x values. Okay, notice they go in twos, so I'm not going to catch negative 1, 1, 3, 5, okay, since these are even going in twos. So it's automatically already discrete because we're missing values in between. But I still need to graph it though. So in order to do that, I want to make a chart or a table with these given values of the domain. So if I plug these x values back in up here in my original function, if I plug negative 2 in there, I'm going to get 0. If I plug 0 in there, I get 1. If I plug 2 in there, I get back 2. And if I plug 4 in there, I get back 3. So again, these are points I can graph. So negative 2, 0. 0, 1. 2, 2. and 4, 3. Okay, so here's our points graphed. And then the last part says, okay, identify the range. Well, we said earlier the range is just our y values. So we just read them from our table, right? So here in the curly brackets, I have 0, 1, 2, and 3. And that is my range. In example 2, we're still going to use the same function, but we have a different domain this time, and we're still going to identify the range. So now our domain is everything bigger than or equal to -3. Well, just reading that to yourself, you have everything bigger than or equal to -3. So you're going to hit -3, -2, -1, 0, 1, 2, 3, on and on forever. And you're also going to hit every number in between the whole numbers, so like the halves. So -2.5, -1.5, okay? So this one is going to be continuous since you're hitting all of those numbers in between. But I still need to figure out a range, okay? So first I need a good starting point. So since it's equal to -3, what I'm going to do is plug in -3 into my function. Okay. So if I do that, I get 0.5 or 1/2 times -3 plus 1. So when I evaluate that, that is -1/2 or 0.5 negative. So starting there at -3 as a point, -0.5. Here I go to graph that. -3 and -0.5 is in between 0 and -1. And then as I keep going, I could keep graphing points. Okay. So at -2, if I plug that in, -1 if I plug that in. Okay. So we already did that on the previous slide, right? So -2, 0. I'll rewrite that table. So we said -2, 0, 0, 1, 2, 2, and then 4, 3. So I can graph those. So since this is continuous, I can connect these. And it's hitting every number in between the whole numbers. So this one is continuous. Our last example here, write and graph the function described. Determine the domain and the range. Then tell whether the function is discrete or continuous. So we have two parts. Give me the domain and the range. Then tell me if it's discrete or continuous. So for this example, a student group is selling chocolate bars for $2 each. The function f of x gives the amount of money collected after selling x chocolate bars. So if I want to think of a domain, okay, well, I got to think of how many chocolate bars that is, okay, because x values represents chocolate bars. So I can't have half of a chocolate bar or 1.5 chocolate bars. These are working in whole numbers, right? So I could sell 0 chocolate bars. I could sell 1. I could sell 2, 3, and as many as I want, right? So here's our domain. But the range, well, I got to think about my y values here, okay? Because I need a function to represent that to see what y values I'm going to get back. So if I try to make a function out of this, it says each chocolate bar is $2 each. Okay, well, chocolate bars represented our x value. Since each chocolate bar is $2, well, that's just like saying 2x, right? So $2 times each chocolate bar. That will be our function because it doesn't give us any other info. So if I think about that, I could plug in any x value, 0 through basically infinity, on and on forever, which, by the way, can be written like 0, comma, infinity with parenthesis in interval notation if you wanted to. So back to the range. If I plug in 0 into x, well, I'm going to get back out 0. If I plug 1 into x, I'm getting back out 2. Okay. If I plug 2 in for x, I'm getting back out 4. Plug 3 in there and getting back out 6. Okay. So if you notice, that's all the evens. So I'm missing some numbers in between that, right? So 1, 3, 5. So automatically, since I'm missing numbers in between, this is going to be discrete. Okay. But I still need to graph that, right? So if I graph that, 0, 0, then 1, 2, 2, 4. If I sell 3 candy bars, well, that's $6. 4 candy bars, well, that's $8. On and on and on. And I can't connect them, okay, because I'm missing some numbers in between, right? So at $3 I'm missing, at $5 I'm missing, at $7 I'm missing on my Y value. Okay, I'm missing those numbers, so I can't connect them. That's why it is discrete. They are broken up by points.